Now we're going to take a look at molecular shapes, that is the shapes molecules take on in a three-dimensional space. And we're going to follow VSEPR theory, which is an acronym, and here's what it stands for: valence, shell, electron, pair, repulsion. And what this means is that valence shells, electrons, repel each other, and so therefore they want to take up as much space as possible. So that's what we're going to follow when we do these molecular shapes. There are 14 molecular shapes. Number 1, linear. An example of a linear molecular shape would be BeF2. What you want to do, first of all, is draw the Lewis dot structure. So here's my example. I'm going to start on the outside and work my way towards the middle. So F has 7. And beryllium is in group 2, so it only has 2. Now beryllium is okay with just 4 electrons. It doesn't have to have the octet. It has 4. And if you look around the central atom, you'll see that there are 2 shared pair and 0 unshared pair around the beryllium, around the central atom. Anytime you have 2 shared and 0 unshared, your bond angle is 180. And this is called a linear shape. So here's what I want you to know. You're going to draw structures. Once you draw the structures, you count up the shared and unshared, and that will tell you the name, which in this case is linear, and the bond angle. So I want you to know the name, linear, and the bond angle. Number 2, trigonal planar. BF3 is an example there. BF3 looks like this. Boron's in the middle. Least electronegative in the middle. All the F's have 7. And boron has 3, and boron is another one that's okay with less than an octet. Well, if you look around the boron, it's only got 6. That's okay because it's a central element. But there's 3 shared around the central element and 0 unshared. So the name is trigonal planar, and the bond angle is 120 because the electrons want to be as far apart as possible. Number 3, tetrahedral. Example CH4. The bond angle is 109.5, and I know it doesn't look like this, but this is a 3-dimensional molecule. So when you draw this, H has 1 and the carbon has 4. So around the carbon, there are 4 shared pairs of electrons and 0 unshared. This is not a flat molecule, and I'll show you the actual models in class. But this is a tetrahedral, bond angle is 109.5, even though it really doesn't look like it in this case. Number 4, trigonal pyramidal. NH3 is an example. Hydrogen has 1, nitrogen has 5. Okay, if you look around the central atom, we have an unshared pair right here around the nitrogen. An unshared pair takes up more space than a shared pair, so this bond angle, instead of being 109.5, it's actually 107. But this is a trigonal pyramidal. 3 shared, 1 unshared pair. Number 5 is a bent molecule. Examples: water, oxygen has 6 valence electrons. If you look around the central element, you'll see there's 2 shared, but there's 2 unshared that aren't bonded to anything. So I've circled the unshared pairs. The bond angle, that is the angle between the hydrogen here, is actually 104.5. And I know, again, some of these don't look like the bond angles, but I'll show you the models in class to show you what they actually look like in a 3-dimensional space. Number 6 is linear. Has no bond angle. Example, HF. Anytime you only have 2 elements bonded together, like HF, there's only going to be 1 bond right here. Anytime you only have 1 bond, 1 shared pair, you're not going to have a bond angle because there's not 2 bonds. There's only 1. So there's no bond angle here, just 1 bond. Anytime you have 2 elements bonded together, and they have to be in a line. And number 7 is bent. And this is the second bent molecule. But O3 is bent. When you draw this structure, there has to be a double bond. in order to get all elements to have 8 valence electrons. But a double bond counts as one. So this is one shared pair, here's the other shared pair, and then you've got your unshared pair around the central element. Bond angle between these oxygen is 110 degrees. Okay, so those are the 7 shapes that more or less follow the octet rule. But there are expanded octet shapes as well, where the central atom can have more than 8 valence electrons. Example, number 1, square planar XeF4. Now the fluorine have 7. I'm not going to draw all the 7 around the F's because it just gets messy. I'm just going to draw the 1 there for the F's. And then xenon has 8. One of its electrons is going to go to each fluorine to give fluorine 8 valence electrons. So each fluorine now has 8. But then you've got 4 pair that are left over that you just kind of have to put around the xenon. So you got your 2 unshared pair around the xenon, plus you got 4 shared pair. This is going to take on a square planar molecule. Bond angle is 90. But this is expanded octet because the xenon has more than 8. Number 2 is a linear molecule. We've already had a couple linears. This is the third linear. XeF2, again, without drawing all the dots around the fluorine, we'll just put 1 there for the F. Now xenon has 8, so 1 there, 1 there. It's got 6 more left over. We're just going to put around the xenon. And you'll see that around the central atom there are 3 unshared pairs, but this is a linear molecule, so the bond angle between the fluorines is 180. And that's what makes it the linear shape. Number 3 in the expanded octet is trigonal bipyramidal. This has 2 bond angles, PCl5. 2 bond angles. And again, when you draw this on a flat surface, it does not look like it does in a 3-dimensional space. But PCl5, without drawing all the ones around the chlorine, chlorine has 7, so I'm just going to put 1 there. P has 5, so it works out really nicely because phosphorus is going to donate 1 to each chlorine. There's 5 shared pairs of electrons around the P, 0 unshared. And this is a trigonal bipyramidal with the 2 bond angles, 90 and 120. Number 4, octahedral, SF6. There's going to be 6 fluorine bonded to the sulfur. And again, to kind of not make this as messy as possible, we're going to make it neat here. The F's have 7. I'm just going to draw 1. And then the sulfur has 6. So it works out really nicely because the sulfur gives 1 valence electron to each F. The sulfur has 6 bonds, 6 shared pairs, 0 unshared. Bond angle is 90, and that's an octahedral shape. And again, I'll show you the 3-dimensional molecule in class. Number 5, square pyramidal, IF5. F has 7. We'll put 1 there for each F to kind of clean up the molecule. I has 7. 1 goes to each F to give F the 8. But then I got an extra pair left on the iodine. So I've got 5 shared and 1 unshared pair. It's a square pyramidal shape. The bond angle is 90. Number 6, T-shaped planar, BRF3. BR is in the middle, F on the outside. F has 7. I'm going to draw 1 for F. BR has 7. 1 goes to each fluorine to give fluorine the 8. And then you've got 4 left over. So you got 2 unshared pairs around the bromine. 3 bonds, 3 shared pairs. It's a T-shaped planar, and the bond angle is 90. And then finally, the 7th expanded octet shape. Irregular tetrahedron, or the seesaw, SCl4. Cl has 7. We'll just draw 1. Sulfur has 6. 1 goes to each chlorine to give chlorine 8. And then you've got an extra pair left over. So you've got an unshared pair plus 4 shared pairs. That gives you the seesaw. And this has 2 bond angles, 90 and 110. So I will show you the actual 3-dimensional molecules in class. because when you draw these on a piece of paper, on a flat surface, it does not look like they do in reality. So I'll show you the actual models, but what you need to know for each time you draw a Lewis diagram, you need to know the shape, the name of the shape, and the bond angles. So there is quite a bit of memorization for this particular section.